A discrete probability distribution that we have seen, isn't it? In case of linear combination state, we had a probability of getting energy E1, energy E2, like that. Or in case of head or tail, uh, probability of being head, tail. It's a kind of discrete distribution. We have seen continuous distribution also in case of mod psi square, which is probability density of finding the position and all, isn't it? Again, we shall talk about that discrete probability distribution. In that one, we have to define one random variable, okay, and probability of finding that variable actually. Let me try to quickly give that one, because using that one I can define variance, I can define what you call standard deviation of that variable and all, okay. Those are quite important. Standard deviation is quite important part of yeah. Now suppose if you toss a dice, okay, and so when you toss that one, you got 6 possibilities. Let me take it as a score, okay. Now that score can be either 1, 2, 3 and so on up to 6. Is that okay? Or if you toss a pair of dice once, okay. Now again your score can be between what is that, 6 plus 6, 12 to 2. Okay, so 2 to 12, am I right? The minimum score can be 2, maximum score can be 12, isn't it? When you add them, isn't it? Now you can take that one as a score as one variable, because again it can have possible values. We call that one as random variable. Is that okay? So now again you can define probability of getting particular random variable. Isn't it? So in case of a dice, so when you throw die, all of them have same probability, right? Probability of getting 1 is same as getting 2 and so on up to 6. So we can say all of those random variables have the same probability. We can find the average if we define probability, okay? So now once we define that random variable x1, x2 and so on up to xn, okay, that random variable can be anything actually. So suppose if you toss a pair of dice, okay, that random variable can be getting sum equal to 7, or getting sum equal to something like that. You can or so sum is a random variable. You can take sum as a random variable like that. Is that okay? Again, there are many possible ways. So once that random variables are defined, and once again let me take it as 1, 2, 3 and so on up to n here, okay. And let me take it as again probability of getting x1. I can define this one, am I right? Once I define that variable, just like once I define, suppose I'm tossing 2 coin once, am I right? So what is the possibility? Head tail, tail head, tail tail. Here I can't put any variable as a number and all actually, isn't it? I can talk only about statement here. I can't talk about number. Dice is the good idea. Now again, if you toss pair of dice, this again this random variable may be score, whatever you have scored. You can define probability of getting particular score. Are you getting my point? Now look at here. So what is the probability of getting score 7? Probability of getting score again. So pair of dice thrown. Is that okay? Pair of dice thrown. Okay. Now again, your random variable x is equal to sum. Okay. So I call it as a score actually. Okay. Your random variable that can be sum of whatever the outcome that comes out of those 2 dice. Is that okay? Now you can talk about probability of getting 2. Am I right? Minimum score that you can get is 2. Am I right? 1 and 1. When both of individual die gives 1 and 1, you get minimum score 2. You can talk about probability of getting 2. You can talk about probability of getting 3 and so on. You can talk about probability of getting 12. When both are 6 and 6, you get 12, isn't it? Now look at here. What are these probabilities? What is probability of getting 2? First one 1, second one 1, isn't it? only one possible thing in the sample space. What is the total number of possibility in the sample space? Again 36. 2 dice, am I right? So first die can have 6 possibility, after the second die can have 6 possibility. According to principle of counting, we should multiply to get total number of possibility, isn't it? Now I think to get what is the probability of getting 2? Again, how did you say 2 by 36? So there is only one possibility, 1 and 1, am I right? First die can give 1, second die can give 1. There is only one possible outcome. What is the probability of getting 3? Suppose first die can again give pair of dice. Okay, you can put the paint on that one. Suppose red die, green die, isn't it? Are you getting my point? Okay. So first dice and second dice. You can put name for that one. Okay. So first die give 1, second die give 1. Okay. Second die give 1, first die give 1. There is no other possibility. Only one outcome, isn't it? Out of 36. Okay. So what is the probability of getting 3? So that's why that's equal to 1 by 36. Is that okay? 1 by 36. So probability of getting 3 is, look at here, first die can give 1, second die can give 2, and first die can give 2, second die can give 1. You got 2 possibility. Is that okay? Like that. Again, you have to write 2 by 36. Okay. This probability need not be always equally distributed, isn't it? If you choose your random variable as a score, this is my random variable. Okay, this is my random variable. Now I can define probability of xi, where xi running from 2, 3 and so on up to 12 in this particular experiment. Okay, now I can define probability of all of them. So again, what I was thinking is, I was just thinking about this a random variable in any experiment and probability of getting that random variable, getting some particular random variable. There are many, again, that variable can have many assigned value. Again, you can define probability. Now look at here, why I have defined, because once you define random variable, you have a way of taking the mean value. What is the mean of the sum, or what is the mean of the score that you can get if you do large number of trials? How do you get mean value? Can I write x mean? That's equal to summation over xi into probability of getting xi. We call that one as weightage mean, or we call that one as weightage sum or something. I think we have used this kind of formula, am I right, in case of quantum mechanics. Mean value of the score or mean value of that random variable you can define like this. Okay, so mean value of square of that random variable you can define like this. Is that okay? Now this p of xi, we call this one as distribution function. Now this is a discrete. Now I'm talking about discrete distribution. We call that one as a distribution function. Actually, we can call it as probability density function also, or probability distribution. It's simply called as probability distribution. P as a function of that random variable. You can define mean of that random variable. You can define mean of square of that random variable, isn't it? Then you can define standard deviation. Remember it. How do you define standard deviation? Summation over mean deviation the whole square the mean. Am I right? Deviation from the mean, xi minus mean value the whole square. Am I right? Now this again depends on xi, this mean value. Any function of xi, you can take mean value like this, isn't it? I think I have written this one. Some f of x mean that can be written as f of xi into p of xi. Am I right? I have written like this. Do you remember? Any function. Suppose if you need x cube with the mean, you can just substitute it over there, isn't it? So the same idea I'm going to look at here. What is the mean deviation? Individual value. How individual value deviates from the mean. Am I right? This is mean deviation. Mean square deviation. Okay, actually, again, you should take square. I need variance actually. Standard deviation the whole square. Okay, mean of this one, am I right? This is nothing but variance is nothing but variance in x. We have other formula. Let me define other formula, but that can be derived out of this one. Look at here, that's equal to summation over, okay, variance in x, mean deviation xi minus mean x the whole square. Okay, it's mean. This one you have to take mean, then you have to put it into here, and you have to put p of xi. You got mean of this value, isn't it? Variance is nothing but xi minus mean x the whole square, the mean. How do you take any mean? Just put it into that again. So just put that variable and multiply with respect to probability. You got the mean. Now any mean value you can take it in this fashion. Am I right? Look at there. Again, I need a variance is nothing but standard deviation or mean deviation. Okay. Mean, this is deviation from the mean. Am I right? The whole square, the mean, we call that as variance in x. That can be taken in this way. Now what I am saying is that variance in x, that's equal to, what is this one? Xi minus x mean whole square, the mean. Okay, that will talk about how individual points are spread. Am I right? Variance or standard deviation square, that talked about spread of the distribution. Actually it has some physical meaning. Okay, that's equal to summation over I xi minus x mean whole square into p of xi. This is same fashion. Any function, its mean, that function should be placed here respect to probability. You can just sum it up, isn't it? Now standard deviation, that's equal to root of variance. Root of variance in x, that's equal to root of this one. And what I'm saying is this one have got one more way of writing this one. Am I right? What is this one? X square the mean minus x mean the square. It can be derived, isn't it? We have seen that one. So that's why again standard deviation, that's equal to root of variance in x. Okay, that's equal to root of x square the mean minus x mean the square, where x square the mean is this one, x mean is this one, the whole square. This can be applied anywhere, not only in any particular thing. You can define random variable and you can apply all of this formula. I hope this is just a recall of whatever we have done in quantum mechanics. Okay, yeah, now we shall take one small exercise, experimental exercise. Okay, then we shall try to define a theorem, a binomial distribution. So try to define a distribution. Again, I needed that idea. This p of xi, we call that one as probability distribution. Xi is some random variable. Xi you decide using sample space actually. Again, first you construct the sample space, just like earlier when a pair of dice tossed, isn't it? Okay, what is xi? That's a sum of, okay, so that's a total score. That total score depends on your sample space, am I right? Okay, so that's why, again, domain of this function that is defined by, again, that is decided by the sample space actually. Okay, xi are decided by sample space. That random variable is always decided by sample space. If you see, I think NCERT textbook, he gives that kind of definition. Okay, but we need much application here. We call this as probability distribution usually of some random variable xi. Now I wanted to convince that one. That's what the distribution, the word came because of that. Okay, so before directly getting into binomial distribution, again my target is to discuss this one. Okay, binomial distribution. Binomial distribution, is that okay? So we shall start with one example as we do always. Okay, so if you toss a coin thrice, okay, tossing a coin thrice, okay, what are the sample space? Head, 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 tail, head, tail, head, head, tail, tail, isn't it? Tail, head, head, tail, head, tail, 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 head, tail, tail, tail. Am I right? These are the samples. So these are the sample space. Okay. Tossing a coin thrice. First toss, second toss, third toss. Is that okay? First, second, third toss. Is that okay? Tossing a coin thrice. And obviously, all of these elements of the sample space, those should be equally probable. That's why. So each of them carries probability 1 by 8. Am I right? Speak up. One by 8. Now let me define this probability. Okay, probability of getting 3 head 0 tail. What is this one? I'm not talking about order here. Okay, while defining this probability, I'm not worried about the order. Again, obviously, probability of happening of 3 head in an order, that's only one order possible. Okay, that's equal to 1 by 8. Am I right? Write that one. So similarly, probability of getting 2 head 1 tail. What is this one? Speak out. 2 head and 1 tail. I'm not saying 2 head in successive order like that. Okay, I said totally out of 3 trial, 2 head and 1 tail. I'm not talking about order here. Is that okay? 2 head 1 tail. 1, 2, 3. Isn't it? 3 by 8. Speak out. 3 by 8. You have to add those 3. Yeah. So now similarly, probability of getting 1 head 2 tail. Obviously, if you get only 1 head, other 2 will be tail, isn't it? Yeah. Speak out. 1 head 2 tail. 2 tail. 2 tail 1 head. 1, 2, 3 again. 3 by 8. So check that out. Similarly, probability of getting 0 head 3 tail. Is that okay? That's equal to, speak out, 1 by 8, isn't it? When you add, you should get 1 actually. Is that okay? You will get 1. Now look at here. What I do? Yeah, I calculated probability. Remember, in these two probability, I am not talking about order. Out of 3 trial, okay, what is the probability of getting 2 head 1 tail? I am not talking about order here. Is that okay? So that's why I have added them, isn't it? So there is a 3 different way of happening 2 head 1 tail. Am I right? So 2 head 1 tail, 2 head 1 tail, 2 head 1 tail, isn't it? Check this out. Now look at here. What I do is I am going to take this one. Half plus half 3. A plus B 3. Binomial expansion of A plus B whole power 3. Binomial expansion. Write in terms of binomial coefficient. Is that okay? Speak out. 3C0 half raised to 0 half raised to 3. You know A plus B whole power n, binomial expansion.
How can you directly say that half plus half? I mean, is it like 1?
Yeah, it is 1 only, but I need these things. Just see the expansion. It's not complete argument. Okay. So 3C1, okay, half raised to 1, half raised to 2, isn't it? Binomial expansion, okay, of A plus B. So 3C2 half raised to 2, okay, other half raised to 1. So last term is 3C3 half raised to 3, other half raised to 0, isn't it? Check this out. Speak out. Is that okay? Yeah. Now observe this one. What is this value? Write down this value. 3C0. What is 3C0? 1. 3C0 is 1. Isn't it? This whole thing is 1 by 8. Okay. 3C1 is 3. Yes. This whole thing is 3 times, again 1 by 8 only. 3 by 8. This whole thing is, so check this out. Again 3 by 8. This whole thing is again 1 by 8. Is that okay? Check this out. Now look at here, what I am going to say here is that okay? So this whole thing is this probability. So this whole thing, whatever I have written here, okay, this is this probability. Is that okay? This whole term, okay, I'm talking about this whole term. I'm talking about term-wise here, okay, this whole term, and this whole term, okay, and this whole term is this probability, isn't it? This whole term is this probability. This term is this probability. So check this out. Now can you grab one logic here? Here 0 head, okay, 0 head, 3 tail, okay. So in this case 1 head, okay, 1 head, 2 tail, isn't it? You can take this first half as probability of being head, second half as probability of being tail, isn't it? You can define for one toss, this half is probability of getting head, probability of getting tail, isn't it? You can take one as head as one as probability of being head, other as probability of being tail, isn't it? So like that, look at here, this one, so out of 3 trial, okay, out of 3 trial, 2 head, 1 tail. Is it okay? So this one out of 3 trial, okay, so all 3 head, okay, 0 tails. Is that okay? So now look at here, we will get into the binomial distribution where look at here, you better write some statement here. Can you write binomial distribution, some statement here? Just observation, okay, just observation. These probabilities are actually terms in the binomial expansion of half plus half raised to 3, okay. Let me write this one as probability of head plus probability of tail whole power 3. Is that okay? This whole term I am going to write probability of being head plus probability of being tail whole power 3. Obviously it is equal to 1. In case of one toss you will get either head or tail, isn't it? Speak up. So now my basic idea here is observing that in the binomial expansion of this one, okay, what are the terms that comes here, okay, those are the terms which defines these probabilities actually, or these probabilities are out of this binomial expansion. These probabilities are terms in the binomial expansion. Can I say like this? Now, so try to grab the logic here, look at here. So now the next idea is, so define this binomial distribution. Just remember this fact, okay? These probabilities, binomial distribution, it is concerned with trials of repetitive nature. It is concerned with trials of repetitive nature. Okay, trials of repetitive nature in which, okay, in which only occurrence or non-occurrence, in which only occurrence or non-occurrence, okay, success or failure, success or failure, acceptance or rejection, acceptance or rejection, yes or no, no, of a particular event is of interest. Remember, in this case, look at here, what we have done, we have tossed the coin in this case, okay, thrice, am I right? It's a kind of repetitive nature, isn't it? So this whole thing, so it's a trial of repetitive nature, isn't it? Again, we are repeating the trial, isn't it? If you take tossing a coin, we have done 3 trial here, isn't it? We have done so what you call, so 3 trial. Look at here, it is concerned with the trials of repetitive nature, one thing, okay, and so in which, okay, in each of occurrence or non-occurrence of something, okay, success or failure of something, okay, acceptance or rejection, yes or no. Is that okay? Each of those trials should have only two possible outcomes, okay, or each of those trials should be divided into only two possible outcomes. Is that okay? In that case, we can define binomial distribution. So look at here, whatever we have learnt earlier, what we do is, now before defining, let me define. So let me take this success or failure. Is that okay? Let me take success or failure.
So in this whole this kind of conditions.
You can apply binomial distribution. Binomial. Only two types are there, am I right? Two possible outcomes of one trial, isn't it? That's why we call that binomial. Suppose if there are three possible outcomes, you have to define trinomial. You can do that one. Quite lengthy. Is that okay? Yeah. Now look at here. Let me define P as probability of success. In one trial, okay? In one trial, just like this, half is a probability of being head, isn't it? In case of one toss, isn't it? Speak out. So similarly, Q is probability of failure. Is that okay? Let me define this one. Obviously, P plus Q should be equal to 1. Or Q should be equal to 1 minus P. Isn't it? Now look at here. So again, it's a repetitive in nature. After n trial, okay, the question is, what is the probability of our success? Is that okay? We are going to write that probability like this. Probability after n trial R success. We simply write like this. Is that okay? If there are R success, okay, so there should be n minus R failure, remember. Is that okay? If there is R success, okay, out of n trial, if there is R success, so that should be n minus R failure. Is that okay? This probability is equal to probability of n minus R failure. Is that okay? But we don't write other part, okay? We write only one part. That is always sufficient. Is that okay? After n trials, okay, each of trial have got two what you call possibility. One is success and another one is failure, okay? And I defined probability of success and probability of failure, okay? After n trial, the probability of R success, R is a number here, okay? R is a number. Probability of getting R success after n trial, so that we are going to write Pn after n trial R success, that's equal to, look at here, NCR, okay, probability of success raised to R, okay, probability of failure, 1 minus P is probability of failure. If P is the probability of success, 1 minus P is probability of failure raised to n minus R. Number of failure, number of success. Is that okay? So this is the general definition of binomial distribution. Why do we need this one, isn't it? Why can't we find using this one? Look at here. In case of 3 trial, you went for sample space, you found 3 by 8, 1 by 8 like that. Am I right? Earlier. But suppose if I toss a coin 10 times, isn't it? In that case, it was very easy. Am I right? So why do we need this distribution, isn't it? Why do we need to define this distribution? Suppose, so let me take a question. If I toss a coin 10 times, okay, what is the probability after 10 toss, okay, 6 head? Then how do you create the sample space? How do you count that one? If you toss a coin 10 times, what is the number of element in the sample space? Pick out, someone in Google Meet. If I toss a coin 10 times, what is the total number of element in the sample space? I hope you can remember this one, okay? We shall apply this one.
2 power 6.
2 power 10, isn't it? So here you have 8 to power 3, isn't it? Or, so you are tossing 3 times, am I right? Apply principle of counting. Each of toss have got 2 possibility. Total number of possibility should be, each of the toss should be of 2 possibility. You are tossing 10 times, am I right? So again 2 into 2 into 2 and so on up to 10 times. Apply principle of counting to count total number. That's why it will be 2, again your number of element in the sample space will be 2 power 10. You can't go for sample space. Here you can go for sample space. Quite easy. Rather than writing this binomial distribution. But why we need to write this one? Because our ultimate aim is to apply this one for large number of trials. Not only this one, okay, very large. I'm not talking about even 10 trial, okay. So to a very large. That's why if I toss a coin 10 times, okay, let me, what is the probability, okay? What is probability of 6 head? Okay, so 6 head means 4 tail, am I right? So to answer this kind of question, this binomial distribution will be very helpful. Now, so how do you apply this whole thing to this one? You have to define probability of being head as success, probability of being tail as failure, isn't it? Only 2 things are there. And then you can apply this one, isn't it? Because this definition, we have defined the binomial binomial distribution definition by defining probability of success and failure, isn't it? So that's why, again, among these 2, you treat one as success, other as failure, okay? Suppose I am tossing the coin, you said head, isn't it? Then if head comes, that is your success, isn't it? Like that. Among these 2, treat one as success, treat other as failure. Is that okay? We shall try to solve that one, okay? Now, look at here. Let me try to answer this question now. A coin is tossed 10 times, am I right? N is equal to 10. N is equal to 10. So now, let me write probability of head, that's equal to small p. Let me take head as a success, okay? What is that one? That's equal to half, isn't it? So now, similarly, so Q, which is probability of failure, isn't it? That's equal to P of tail, am I right? If tail comes, I will take it as a failure. It's your choice. You can take reverse. It's all your choice. That's equal to half again. So that's why probability of getting 6 head, that means I have taken head as a success here, okay? Let me take this one as success. This one as failure. Is that okay? Probability after 10 trial, okay, 6 head. That means 4 tail, okay? 6 head, 4 tail, okay? So because we know what is the total number, if you write 6 head, that means the rest of them should be trail. Is that okay? Only 2 possibilities are there. That's why. So this is nothing but probability after 10 trial. How much success? 6 success. Am I right? Probability of getting R success out of n trial. Okay. So head I have taken it as success. That's equal to 10C6. Okay. Probability of success raised to 6. 1 minus probability of success. That means this whole thing is probability of failure actually. Or you can write as Q also. You can write this one as Q. 1 minus P equal to Q. Is that okay? So write down in the other way. Raised to, so 10 minus 6. Okay, what is this one? 10C6 half raised to 6 half raised to 4, isn't it? In this case, you can't even imagine of going to sample space after 10 trial, isn't it? You need to go for 2 power 10 different elements of the sample space. Then you need to count, isn't it? Is that okay? So try to apply to this question. If a coin is tossed 10 times, what is the probability of 6 head, 4 tail? Yeah, speak up.
So in binomial distribution, we are not interested in order.
No. Again, we are not talking about order here. We are not saying 6 head should come in the first order like that. Okay, we are not talking about order. We are counting total number of success, total number of failure in any order. Is that okay? So actually, this is the number of order. This 10 factorial divided by, okay, 6 factorial, 4 factorial. Am I right? This one. What is this one actually? That's a good question. Okay. So this one actually, out of 10, 6 are of one type, 4 are of other type. Am I right? This is the different way of permuting them. And we have added all of them. Speak out. Are you getting my point? This binomial coefficient actually. So again, let me write in a general way. Okay. This binomial coefficient. So NCR. That's equal to n factorial divided by r factorial n minus r factorial. Am I right? That means out of n, r are of one type. Okay. N minus r are of other type. This is the different way of permuting them. This is the different number of order. I mean, number of ways of getting r success, n minus r failure. Is that okay? And we have multiplied with that number. That means we counted all of them. We are not talking about order here. Is that okay? Speak out. If you talk about any one order, it would be 1 by 2 power 10, I think, isn't it? Check this out. If you talk about any one of these, obviously you will get 1 by 8 here, isn't it?
No, sir, can you repeat that part?
Which one?
Multiply it.
Now, multiplying means, again, look at here. In case of 2 head, 1 tail, look at here, we have added this probability, and this probability. Am I right? We added. Once you add, it will be irrespective of the order. Isn't it? Again, once you add, you are talking about probability of getting 2 head, 1 tail. You are not talking about order, isn't it? Once you add them. Suppose if you talk only about this one, okay? What is this one? This is probability of getting first 2 head, second one is tail. Sorry, third one is tail. Isn't it? Are you getting point? When you add them, adding them is nothing but multiplying how many numbers, isn't it? So this is the total number of ways of getting 6 head, 4 tail out of 10 trial. And that is the binomial coefficient actually. You better read Reef actually. In Reef, he is going to derive binomial distribution in this way actually. Now, I just went for some example and I defined here, isn't it? So he don't do that one. He apply these ideas to derive binomial distribution. Is that okay? Speak out. It is irrespective of order. When you take the summation, it will be irrespective of order. You are talking about summation of all of those possibilities. Is that okay? So remember this what you call logic. Whenever you make summation over different what you call possibility, you will get irrespective of them actually. Are you getting my point? Speak out. You will apply this one, this concept, whatever I told now. Okay? Yeah, speak out. So observe this one. This whole binomial coefficient is number of ways of getting r success and n minus r failure. So now probability of getting r success. Yeah, wait 1 second. Probability of getting r success, okay, and n minus r failure. Okay, let me write this one as NCR p raised to r q raised to n minus r. Okay. Again, you have done n trials, isn't it? This is how again it is derived in the Reef. Okay, you have done n trials. Am I right? So out of them, you got r success, n minus r failure. Okay. Let me think. First r success. Okay. First r trial you got success. Next n minus r trial you got failure. Let me take like that. Okay, for a time's sake. Okay. So then, what is the total probability? You have to write p into and so on up to r times, isn't it? So it is one after other. Am I right? These events are one after other. This one and this one. Event 1 and event 2 and event 3 and so on up to event n, isn't it? And comes here. That's why you need to multiply the probability, isn't it? So let me take first r trials you got success. Okay. And total probability I need to multiply the individual one. Okay. So next n minus r q into and so on up to n minus r. Is that okay?
Yes.
Now look at here. This is one of the way of happening of r success, n minus r failure. Is that okay? So that's why we are not concerned about order. This is one order. Am I right? This is one way of distributing them. So now, how many of these things are there? How many of r success and n minus r failures are there? So that is n factorial divided by n minus r factorial, okay? This many different what you call things are there where you will have R success, okay, n minus R failure, isn't it? That's why you multiply this one with this one. What is this one? P raised to R. So Q raised to n minus R. And you get total probability. Probability of getting R success after n trial irrespective of the order. Order doesn't matter. Is that okay? If you talk about one of those order, you just take this multiplication. Is that okay? This is how he derives in the Reef textbook. Read that one after this class. Is that okay? Yeah, speak up.
Sir, how much probability comes there and substitute minus R?
No, out of n, this much of one type, it's a permutation with repetition. Out of n, n1 are of one type, n2 are of other type, isn't it? Out of n trial, n minus r of one type, that means which are succeeded, am I right? N minus r are of other type, isn't it? Just like head and tail. This is your permutation with repetition.
In the first part, we are doing permutation with repetition, and we are multiplying with p power n r q power n minus r. What is that? What I mean?
No, you have to start with this one, then you have to multiply this one. In the derivation, you have to start with this one. In one of the order, okay? In one of the order, this whole thing is the probability of getting that particular order. Now I need irrespective of the order. That's why I need to sum up all possible such orders. Am I right? How many ways that you may get what you call this much success, this much failure in this many ways. But I'm not concerned with order. Then I need to what you call make the summation. Is that okay? Speak out. So take the simplest example, then it will be convincing. Am I right? I need probability of 2 head, 1 tail, irrespective of the order. Then what I did? I have taken this one, and this one, and I have added the probability. Once I add the probability, what I got? I got probability of getting 2 head, 1 tail, irrespective of the order. Isn't it? So take the simplest example and try to convince yourself. Is that okay? Speak out. When you add, okay, again 2 head 1 tail, when you add what you call probability for different possibility, you will get irrespective of the order. 3 by 8 is probability of getting 2 head 1 tail irrespective of the order. We have taken different order, we have added their probability. Speak out. No, that's what I'm saying. After 10 trial, probability of getting 6 head is that's equal to, okay, that's equal to 10C6, okay, 10C6, probability of getting head raised to 6, okay, 1 minus probability of getting head raised to 10 minus 6. You can take it as a success, you can take this one as this whole thing as failure. That's what I have written. This is half and half, you will know that one. Speak out. It is irrespective of the order, okay? If you are talking about one of the order, then only this part was your probability, okay? This was your probability, okay? You are summing up all of those different ordered what you call probabilities, okay? You will get irrespective of the order, okay? Try to grab that idea. That's a good question.
Combination. So
No. Yeah, it counts sum of all possible combinations of R success, N minus R failure. That's correct. It is a sum only. You have to take that sum of this one this many times. Then you multiply with that one. Am I right?
we are not doing the summation, but it counts all possible.
All possible order of R success, N minus R failure. That's correct. Okay?
Okay.
Yeah.
Okay.
You have to sum up this one these many times, isn't it? This one plus this one plus this one and so on this many times. Then what we do? We multiply with that factor, isn't it? Yeah, that's what we did here. Okay. So now look at here. One more thing you need to observe. Okay. So this is again we better write this one like this: N C R P raised to R Q raised to N minus R. Is that okay? So now let me write summation over R is equal to 0 to N. So P N of R. Can you grab what is this one? Speak out. NCR P raised to R q raised to n minus r. What is this one? Speak out.
So
This is p plus q whole power n. That means this whole thing, whatever we have written, this is one factor of binomial expansion of p plus q whole power n. That's what I was trying to show, half plus half whole power n. Obviously, this is 1 only, okay? And this is a normalization. You don't have to take care, it is normalized. Is that okay? It's just like total, either you get 0 success, 1 success, 2 success, all are success, am I right? And total probability should be equal to 1, isn't it? Now this r becomes a kind of variable, am I right? It can be 0, 1, 2 and so on, isn't it? Whenever we define probability of some variable, am I right? Just as we did, I think, first chapter of Griffiths, am I right? We can find mean value. Speak out. Can I write R mean? Mean value of success. How to write that one? Let me define this one again in case of random mock problem. But before that, I better to define mean value. Mean success, okay? Mean number of success, okay? Mean number of success. That means to find this mean number of success, you need to take that n trial many times. And each of the time you have to check for how many success you get. Then you have to take the mean. This n trial you have to do many times. Is that okay? Infinitely many times. So that's equal. Let me write R mean because I have taken R as a number of success. Am I right? That's equal to, you can write like this, summation over R is equal to 0 to n, R into probability of R. Am I right? Isn't it? Can you grab this one? In case of any random variable, okay? You can write statistical average, isn't it? We call this statistical average. You remember? And summation over all possibility. All possibility means R should be 0 to n, okay? So similarly, you can define. So what is this one? Can you quickly tell me? Can you do this one? Or let me do it again in case of random mock problem, okay? Similar expressions. Summation over R is equal to 0 to n, R into NCR, P raised to R, 1 minus P or Q raised to n minus R. Let me write it directly, okay? We shall do it later. Anyway, there I need to do that one, okay? We shall do it later. Or try to grab some logic. This is equal to n into P. It's not surprising, am I right? Average number of success is equal to total number of trials multiplied with probability of being success. It's a kind of logical, isn't it? Are you getting my point? P is the probability of success, n is the total number of trial. When you multiply total number of trial with the probability of success, you will get average number of success. Isn't it logical? So similarly, mean number of failure. Mean number of failure. That's equal to 1 minus R is a failure. Am I right? Sorry, n minus R, not 1 minus R, isn't it? N minus R is failure. So this will be equal to n into Q. Total number of trial into probability of failure, you will get mean number of failure. Now, along with this, we are going to define standard deviation actually. What is standard deviation? Any idea? Root of R. Again, similarly, look at it, similar to this one, you can define R square mean, am I right? That's equal to summation over R equal to 0 to n, R square into Pn of R. Check this out. You can do like that. So using these two, you can define sigma, that's equal to root of R square mean minus R mean square. Is that okay? This one is equal to root of npq. We shall derive this one, okay? In case of what you call next topic. Write down, just simply write down, okay? For a time sake. Standard deviation in the success, number of success, okay? Standard deviation in the number of success. R is the number of success, not any displacement or radius or something, okay? Be careful. Be careful with the notation here, okay? And square of that one, we call that one as variance actually, okay? VA, variance in R, okay? We are going to write as NPQ, or that's equal to R square mean minus R mean square, that's equal to root of NPQ. Variance in R. Write down that one. No, yeah, root is not there. Square of that one. NPQ. Now look at here. You better to take one more note here. Now we shall try to apply this one. Before we apply this one, take a note here, okay? Yeah. Speak up.
Sir, in binomial distribution, we always work with equally prior probability.
No. No. Equally prior means all sample space have equal prior probability. But probability of success and failure, they may be different. Here we have taken so tossing coin, am I right? Where head and tail have equal probability, okay? But if you take that after n trial, if you take all sample space, each and every element of the sample space have got same probability, okay? That again, that is true. But this P and Q need not be equal. P plus Q equal to 1. That's it, okay? Yeah, that's why we defined in the most general way, P and Q separately. Is that okay? So this tossing coin is one of the example, okay? Yeah, we shall apply that one for something else, okay? So before that, we better to note down. The note here is, they ask after n trial, okay, what is the probability of getting at least R success? At least R success. I told this at least word will come frequently, isn't it? In case of this probability question, isn't it? What do you mean by at least R success? Speak out. More than or equal to R, am I right? That means this is probability after n trial R success plus probability after n trial R plus 1 success plus and so on up to probability after n trial n success. Is that okay? This one is equal to this one. Speak out. At least R success means either R success or R plus 1 success. Either, isn't it? Either or, isn't it? Either R success or R plus 1 success or R plus 2 success or all success. Is that okay? That means minimum is R, okay? So that's why you need to add all of these probabilities. You will get at least R success. Are you grabbing this logic? This is very important because in question it will come, okay? After n trial, what is the probability of getting at least R success? At least means, okay, least is R, maximum can be anything. Maximum is n actually. Is that okay? Out of n trial. Is that okay? At least R success means probability of getting R success plus probability of getting R plus 1 success plus and so on, probability of getting n success. Is that okay? Now look at here, what is this one? What I do here is, I am going to add this one. So Pn of 0 plus Pn of 1 plus and so on, Pn of R minus 1. I am going to add this one to this one and I am going to subtract with the same. For whole thing, I am going to add this one, okay? And I am going to subtract with the same. Pn of 0 plus Pn of 1 plus and so on, Pn of R minus 1. When you add these two, what is that one? Speak out. 1, am I right? This is total possibility, isn't it? Pn of 0, Pn of 1, Pn of R minus 1, Pn of R, and so on to Pn. This whole thing is 1, okay? This one added with this factor, that's equal to 1. This can be also written as 1 minus, okay, Pn of 0 plus Pn of 1 plus and so on Pn of r minus 1, okay? Sometimes counting this one would be easy, okay, or finding this factor would be easy. Sometimes finding this factor would be easy, isn't it? That's all depends on the situation. Okay, write this whole thing in a different step, okay? I have written there only. You just write in a separate step, okay, in your notes. So probability of getting at least R success, I can write it as 1 minus probability of getting less than R success. Less than R success. I'll talk only about success. Better not to take other part. Other part will come along with it. Probability of getting at least R success, that's equal to 1 minus probability of getting, okay, less than R success. This is probability of getting less than R success. Yeah, we shall see that one. We shall apply that one in a different situation. Then you will able to remember. Okay. Let me start taking the problems. The probability that a pen manufactured by a company will be defective is 1 by 10. Okay. So what should I take? P or Q? Speak out. He's talking about defective. Okay. Let me take that one as P. Okay. P is equal to 1 by 10. Okay. This is example number 26.38 from Gravel. Okay. The probability that a pen manufactured by a company will be defective is 1 by 10. Okay. If this is probability a pen being defective. Okay. So what is Q then? 9 by 10. That means which is not defective. Probability that pen is not defective. Obviously this probability should be low, isn't it? If probability of being defective is more, then why do they manufacture? So of 12 such pens manufactured, okay, N is equal to 12. 12 pens manufactured. That means we had 12 trials here, okay? Yeah. Now the question is, what is the probability? What is the probability that exactly 2 will be defective after 12 manufacturing? Okay, after manufacturing 12 pens, so 12 pens. What is the probability that speak out? Only 2 pens are defective. What is the probability that exactly 2 pens will be defective? Exactly 2 pens will be defective. Yeah, so tell me what is this one? That means probability after n trial, 2 pens are after trial, 2 pens are defective. That's equal to 12C2 probability of defective raised to 2. Probability of not defective raised to 12 minus 2. Can you write this one? Can you find this one? Is it possible? Anyone carrying this equal to 12C2 P raised to 2. What is P? 0.1 raised to 2. What is Q? 0.9 raised to 10. What is the answer? Anyone carrying what is 12C2? Anyone carrying calculator? Yeah, anyway, let us keep that one.
66.
No. How it can be 66? It should be less than 1 probability. You got this one 66?
Yes, sir. 12C2.
66 multiplied with 0.9 raised to 10, 0.1 raised to 2. Now next one, probability after 12 trial, okay? At least 2 will be defective. Look at here. At least.
So 0.9
Yeah, let it be, okay? At least 2 will be defective. Okay? Probability after manufacturing 12 pen, at least 2 will be defective. What do you mean by at least 2 will be defective? Speak out. Probability after 12, 2 will be defective. Probability after 12, 3 is defective. Speak out. 4 plus and so on after 12 defective. Are you getting the point? At least many. Speak out. Probability at least 2 will be defective is equal to probability of 2 defective plus probability of so 3 defective and so on, probability of all defective. That is the meaning of at least, am I right? Minimum this one, maximum anything can happen, isn't it? So this one, look at this is quite difficult to calculate now. Okay, then what we do? We are going to add this one. Probability after 12 trial, 0 defective. Probability after 12 trial, 1 defective. And I'm going to multiply with the same. Can you see this part of the board? Okay. Speak out. I'm going to add this one and I'm going to, so actually I need this factor only, okay? But I'm going to add this one, subtract this one. When I add this one, this is 1. It can be written as 1 minus probability after 12 trial, 0 success plus probability after 12 trial, speak out, 1 success. This is easy to calculate rather than this whole term, isn't it? Can you quickly do this one? Is that doable? Is that okay? That factor is 1 minus 12C0, okay, P raised to 0, Q raised to 12, okay, plus 12C1, P raised to 1, Q raised to 11, isn't it? What is 12C0? That's equal to 12, am I right? I think you can do this one. You can put P and Q here, value. That's quite easy to calculate. Practice this one, okay? Now look at it. Let me take one reef problem. Let me upload many problems here, okay? So wait a second. I think I have one more part of this question. What is the probability that none will be defective? Yeah, part C of the question. Wait a second. Part C of the question. What is the probability after 12 trial, 0 defective? None will be defective means 0 defective, isn't it? That's quite simple, am I right? There's only one. 0 defective. What is this one? 12C0, defective raised to 0. What do you call? Q raised to 12 here, isn't it? That you can do. Remember, in book, he might have taken this one as success, this one as failure. Both things will work, okay? You don't have to worry.
But defective is always having in mind it is failure.
Yeah, it is a failure, isn't it? Because we defined our distribution by success and failure, isn't it? That's why, you just follow whatever comfortable for you. But you should remember, probability after 12 trials, 2 pence defective, that will be 12C2, probability of defective raised to 2. That's why I read like that. Just like probability of head raised to 2, probability of tail raised to rest of the order, isn't it? Like that I defined. That's why what I did is, probability that after 12 trial, 2 pence will be defective is, you should get what is the probability of defective first, okay? So now, 12C2, probability of defective raised to 2, and probability, 1 minus P raised to rest of the power. You can define like this, isn't it? That's your choice, okay? I did in my way, you can do it in your way, okay? Speak out. Let me take one more question here. That's a very nice question, which can be solved in many ways, but I prefer applying binomial distribution whenever he talks about occurrence and non-occurrence, okay? Problem 1.1. Six true dice are rolled, okay? 6 dice are rolled. Dice means you know that one, am I right? It contains 1, 2, 3 and so on up to 6, isn't it? So I'm talking about dice here, okay? Okay, 1, 2, 3, I don't know which order, okay? Like that. So 6 of them are rolled, okay? 6 of them are rolled. The question is, what is the probability of getting exactly one ace? Ace means 1, okay? He's talking about 1. Ace. AC. Ace means 1, okay? What is the probability of getting exactly one ace? What is the probability of getting at least one ace? What is the probability of getting 2 ace? Now, it's very difficult to go for sample space and getting this done. And not required actually. Is that okay? He's talking about occurrence of ace and non-occurrence of ace here. Look at here. The question is 6 dice are rolled. 6 dice are rolled. Okay. He's asking probability of getting exactly one ace. Okay. Probability of getting at least one ace. Probability of getting exactly 2 aces. Now he is talking about occurrence of ace, non-occurrence of ace, isn't it? And you have 6 trials actually. Remember, what I do here is 6 dice are rolled together. Am I right here? In this question, whatever he mentioned, 6 dice, you have taken 6 dice, you have rolled them together. Am I right? And you are counting what is the probability of getting only one ace, at least one ace, and what you call so 2 aces. Okay. Now look at here. 6 dice are rolled once. Am I right? That is always equivalent to, okay? It's always equivalent to rolling one dice, okay? Rolling one dice 6 times. Can you agree with this one? Because we always think about repeated trials, am I right? Now, you may think that how it is repeated trial. We have taken only one trial. We have taken 6 dice and we rolled all of them together, isn't it? You may think like this is not repeated trial, but make it equivalent to rolling one dice 6 times. So can you agree with this one? Speak out. One dice 6 times, isn't it? So because again, when you roll 6 dice, okay, each of the dice are independent. Am I right? Each of the dice are independent means again what do you call state of one die, a state of one dice will not decide state of other dice. Am I right? All 6 dice are independent. Like that, while rolling 6 what do you call one dice 6 times in each of the trial, which is independent of the earlier trial, very fresh trial, just like you toss the coin. Is that okay? So that's why these two are equivalent. So can I say like this? That means we have 6 trial. Can I say like this? So probability of getting only one ace here is same as probability of getting one ace here, isn't it? Out of 6 trial. Now look at here. Let me take. So in case of one, let me now solve the problem for this one. That means I solved the problem for this one, isn't it? Now let me take this one. Okay, for this one I have to define probability of ace. Am I right? Let me write it as P simply. That's equal to 1 by 6. Isn't it? When you throw a dice, am I right? Probability of getting 1, okay, that's equal to 1 by 6 because you have 6 possibilities, isn't it? So probability of not getting ace, can I write that one as Q? Q not getting ace. Let me write it as simply Q, that's equal to 1 minus P, that's equal to 5 by 6. And how many trials you have? Okay, each of those events have got this probability. Am I right? Okay, you have 6 trials. Okay, after 6 trial, so only one ace. Yeah, what is this one? 6C1, probability of getting ace power 1 probability of not getting A's power 6 minus 1. I'm applying by, again, why do you count total number to apply basic probability, what you call, idea, am I right? Favor divided by total number. I'm not applying that formula. The total number is what you call 6 into 6 into, yeah. No, not like that, 6 power 6 actually.
6 power 6 will come, yes.
Isn't it? Each of this event have got 6 possibility. 6, again, principle of counting. Apply principle of counting, okay? You should be very good at applying principle of counting. 6 power 6, okay? Yeah. Remember, that's a number of element in the sample space. Total number of element in the sample space, okay? No. Again, if he is talking about probability of getting 1, 2, these two together, then you can't apply binomial, okay? But here he is talking about only occurrence and non-occurrence of something, am I right? So that's why I defined probability of getting A's, probability of not getting A's. Once you define these two, you can apply that one.
Yes, sir, yes.
So try to model this problem again yourself, okay? Probability after 6 trial getting 1 A's, that's equal to 6C1, probability of getting A's raised to 1, probability of not getting A's raised to 6 minus 1, or you can write as 1 minus P also, isn't it? So this is equal to 6C1 is 6, speak out, multiplied with P 1 by 6, multiplied with 5 by 6 whole power 5. Can you find this one later and try to match with the solution manual? There is a solution manual for REEF, okay? But use that one only for answer key, okay? Probability after 6 trial, at least 1 is. Speak up. At least 1 is means probability after 6 trial 1 is plus probability after 6 trial 2 is plus and so on, probability after 6 trial 6 is. This can be written as 1 minus probability after 6 trial 0 is. P6 of adding that one and subtracting that one, isn't it? I hope now you got that idea. This is easy way to calculate, isn't it? Now look at here, probability of at least 1 is equal to probability of getting no is. 1 minus, look at here, probability of getting at least 1 is, okay? Whenever this 1 comes, okay, here, you can write like this. You told complement of that one. Whenever 1 is there, then you can write like that, okay? Yeah. After 6 trial, probability of getting at least 1 is, that's equal to 1 minus probability of getting no is. Isn't it? Probability of getting at least 1 is equal to 1 minus probability of getting nothing. Can you grab this logic? That's what happened here actually. Mathematically it happened like that. Look at here. P6 of 0, that means 0 is.
If at least 2 will come, then 1 minus
1 again, 2 more term will come. Then you can't say that one as no is, okay? That's why I told. You apply that one only in case of 1 and at least 1 case, okay? Probability of getting at least 1 is equal to 1 minus probability of getting nothing. Try to grab this logic because they ask many questions regarding at least, okay? And third question is, this part A of the question, part B of the question, part C of the question is exactly 2 aces. Probability after 6 trial getting exactly 2 aces. That's equal to 6C2, probability of getting a's raised to 2, probability of not getting a's raised to 6 minus 2. That's it. Look at here, how I converted a problem in which there exists a kind of occurrence and non-occurrence. I converted the whole thing into binomial distribution. I don't know how he has done. Okay, check that out. Is that okay? Now let me upload some problems today, okay, on this one.